Stop it. Hello, hello. Turn up.
Hello,
Yeah.
hello.
Yeah.
There you go.
You want a microphone?
I don't know if it's necessary. Do you have a couple?
Yeah. It's mostly for the recording.
Well, for the corner, sure.
Yeah.
This is what first.
Check, check.
You have that thing.
Yeah.
Good.
Okay.
Hello everyone. Hello everyone. My name is Enrique. I'm a senior lecturer here at the University of Auckland. Most of my work is on seismic strengthening of buildings with FRP. I've been doing this job for almost 11 years now. I did my PhD here on FRP anchors, and then I won this big, well, relatively big government grant to look at diaphragms. That was 3.5 years ago. And I was already working with Aniket. He contacted me because of my work on FRP anchors. We connected to ACI, and we have been working together since then. We have a little bit of a change in the program. We also have Garrett with us. Garrett is an engineer at Degenco in LA, and he does the company in general, right? Correct me if I'm wrong. But they do a lot of work on R&D and how R&D is translated into codes, which is, I think, a very good timeline of how things happen from pure research at university and then translated into practical engineering design and then into codes. So Garrett is going to go first. Then I will have a brief discussion about my testing on diaphragms, and then Aniket.
Yeah, I think Garrett will go first, then I'll do some diaphragms, then you'll do diaphragms, then I'll do the rest.
Just to make things easier.
Yes, exactly.
So I think with that we can start, maybe?
So I think that...
Sorry. In the case of an emergency, if there is a fire, if there is an earthquake, the exit is right here. Just go to the pedestrian crossing and go across the road. Easy. The toilets are just here, and I think that's all for me.
Cool. Thanks, Enrique. I'm Aniket Borwankar with Simpson Strong-Tie. I've worked with the company for about 7 years. Before that, I worked as a consulting engineer, was involved in a lot of design projects, joined Simpson. I've done my research in FRP during my master's, so kind of joined Simpson. In my current position, I work a lot on R&D testing. That's how we kind of met with Enrique. But I also work on FRP design projects. So the topic for today is seismic detailing of FRP discussed through testing. And the reason why this topic is important is most of the time we look at FRP as a force-based mechanism where we have a force, we design FRP for that particular force. But there is a next step to it. There is a step of adequately detailing that FRP to actually get the performance that we expect FRP strengthened members to get. So that's kind of what we are going to talk today. And like Enrique mentioned, Garrett was here also for the FIB symposium. So does Enrique with his research and testing, me from the manufacturer side, and how this information is useful to consulting engineers like yourself. I think we are trying to build a story here today. So I think we've already gone through this. So both Garrett and myself and Enrique, we are all involved in several ACI committees. I think we went, maybe one more thing to add, a lot of other people are involved in this, so this is not an effort by just 3 of us. There's OSHPOR is a governing agency in California. They do a lot of hospital retrofit work, so they were involved. KL Structures, Ravi Kanetkar is here, he was involved, and then there's a few more consulting engineers who are involved in this effort. just before we get into the details of testing, we are talking about FRP elements, which is basically carbon or glass fiber reinforcing system. We use a lot of FRP on new slab openings, column confinement, wall strengthening, in-plane shear, out-of-plane mechanisms, and then diaphragms, as well as connections between diaphragms and walls. And we'll go into each one of this subsequently in our presentation today. But with that, I'll give it to Garrett.
All right. All right, good to see everyone. Yeah, as Aniket and Enrique mentioned already, I'm a consulting engineer. So I'm in the US and we do a lot of existing building evaluation and retrofit. My specialty is existing buildings, concrete. And so we have a lot of involvement in the building code development in the US. And the reason I'm here and work a lot with Simpson and others is that there's a big gap in our codes. I think the same in New Zealand probably on how you actually apply FRP in design of an existing building retrofit. And so Simpson, fortunately, has been doing a lot of testing recently, funding a lot of testing, and Enrique has been contributing to that as well, where we're learning things and we're hopefully pulling that into our building standards in the US. Here are a few standards here that you'll note are available for FRP. There's an existing building standard, some of you may be aware, that we use in the US called ASC 41. I believe you have a similar assessment type standard that's based on a lot of the concepts in there. And then there's ACI 440, which tells you how to strengthen the FRP itself. The funky thing in the US is that the FRP standard or code does not talk at all to the existing building evaluation standard. So we have loads and acceptance criteria in ASC 41, but it doesn't tell you how to use FRP. ACI 440 tells you how to design FRP for strength, but it doesn't tie that to the acceptance criteria in ASC 41. So we do have some other criteria that are out there, but again, they're inconsistent. They don't talk to each other very well. In existing buildings in the US, we tend to have a problem with non-ductile concrete buildings. These are usually cast in place, so we're not typically dealing with the precast connections that I know you all have a lot of. But it tends to be light reinforcing and non-ductile behavior in the concrete elements. So the approaches we tend to take for this are either to add strength to the building, which usually means actually adding stiffness. And you're actually trying to limit the amount of deformation demand on those non-ductile concrete elements. Or we're adding ductility, and usually we're doing that with FRP by changing the mechanism. So if it's a shear-controlled mechanism in a column, we're making that flexure-controlled instead and hopefully getting more ductility out of it. So I'm sure all of you are aware of the concepts of ductility and brittleness or non-ductile. In ASC 41, we call something that's ductile as deformation-controlled. It doesn't have to be that ductile to be called deformation-controlled, but it means that we get a ductility factor for that type of behavior. Very similar, we call it an M factor in ASC 41. I think it's very similar to your ductility reduction factors you all have in New Zealand. In ASC 41, it's an M factor. For us in new design, it's an R factor, but it's a ductility reduction factor nonetheless. Now, the standard says if you don't have a table that tells you what M factor you get, then you have to treat that action as force controlled. And what that means is you get no ductility reduction factor in ASC 41. At that point, you're designing based on a capacity-based design concept, essentially. So you're trying to make sure that that is not the governing mechanism in your load path or your system. That's generally the idea. So FRP we think of as pretty non-ductile. We don't think of delamination or rupture of FRP as a ductile mechanism. And we treat that as force controlled, at least right now. What that means is you don't get a ductility reduction factor. You have to design it essentially, that mechanism as being elastic in the FRP itself. So just an example of how we might apply this, and hopefully then we'll show how we're lacking some of this data and how all the other test data that Aniket and Enrique are going to show are going to benefit us. But right now what we do is if typically in an existing building, you might have a concrete column that's shear controlled, right? So it has light reinforcing up the height of the column. It's governed by shear. So an approach that would be pretty common in the US is to try to make that thing flexure controlled. So we're going to use 2 MP over L, basically the moment capacity at each end, assuming a hinge to get the shear demand in the column. And we're going to put enough FRP up the height to change that mechanism. So no longer is it shear controlled, that would be this condition 3 down here with, you see it has an M factor, but it's an M of 1, so you get almost no ductility reduction factor in that anyway in ASC 41. But now it moves up to a 2.6, so you get some ductility reduction factor in your design when you can change that from a shear controlled mechanism to a flexure controlled mechanism. And if you want to add even more ductility capacity, you can confine it in those plastic hinge regions. Again, the FRP itself isn't the mechanism, but we're using the FRP to confine the concrete. And then we have a flexure-controlled mechanism that you can use your Mander model or whatever else to design with. But ASC 41, you can get an M factor for that. The problem comes up when we have things that you can't really easily change the mechanism, right? So in concrete walls, for example, you oftentimes have a very long, squat, shear-controlled wall, and it's not really a reasonable thing to be able to add enough FRP to change it to be flexure-controlled, like with a lot of our columns. So what do you do in that scenario? I mean, if you can get a decent amount of increase in ductility, but if you can't, and you have to remain shear-controlled, we have to treat that FRP right now as a force-controlled action, and that becomes, pretty infeasible, I would say, for a lot of buildings. At some point, you can't add so much FRP that you make the building elastic, right? The building's going to drift how it's going to drift, and you can only add so much FRP to decrease the drift demands. This is the statement ACI 440 that talks about force-controlled behavior. So I'll just talk briefly about the testing going on for walls, and I think there are a lot of tests. Aniket, I think, has more slides on this. But this is a program that Simpson put together at their lab in Stockton, California. And these are, you can see it's a very squat wall, so it's very intentionally shear controlled. And it's meant to be so shear controlled that even after adding FRP, it remains shear controlled, because we want to see how much ductility does it have in that scenario. In this case, you can see that the black line was the control, so without any FRP, the existing wall. And then in this particular specimen, FRP was added, so you can see the increased strength in the red there. And you can see that this particular wall has a little bit less ductility, but it still has a ductile response. It's not degrading as soon as it reaches its peak strength. And that's a really key thing. That basically comes from that detailing that Aniket was referring to and anchoring well enough to where you're holding that concrete together. So you're ultimately getting sort of a crushing mechanism in the concrete, but you're able to get some of that ductility out of the vertical bars that are yielding along with the horizontal bars, and you're holding everything together as opposed to having it, FRP rip off and delaminate and having your degrading strength right away. So this is actually, we're actually developing criteria now for this. Say, okay, if you have a shear controlled wall and it has these conditions, and you anchor it sufficiently well, and that's a key point because we had a specimen where the anchors were not deep enough, and the anchors did, basically nothing for the behavior. The FRP did very little for the behavior. If you anchor deep enough and you anchor to the capacity FRP and you hold everything together, you can get a deformation-controlled response is what we're finding. So in ASC 41, the way we would utilize that information is you have a backbone from your hysteretic curve, your load deformation envelope, and then we're going to pick some key points from that curve to basically get our acceptance criteria. The most important one being the collapse prevention, because pretty much everything is governed by collapse prevention for us. That's kind of our biggest hazard check. I think here you have like a one design level earthquake you check, right? We would have a design level earthquake in existing buildings and kind of a maximum considered type event that we're checking for collapse prevention explicitly. So that tends to govern at least a lot of our designs in California. So just pointing out, I'll wrap up here, but those are key points that you could draw from this actual shear controlled wall test. And that point, again, at the end is going to determine usually the collapse prevention limit. And you see a lot of the other points actually come off of that. So even our life safety limit, which you might use for a design level event, is backing off of that collapse type deformation. So just some points about things that are being developed. I don't want to take too much time here, but we're putting together these criteria. This is from a pre-approval that we've been working on with Simpson on hospital review agency. We're hoping to clarify a lot of those actions and how you treat it as deformation controlled or force controlled. So to be continued. Aniket, I'll transfer over to you.
Cool. Thanks, Garrett. So the next part, we are going to kind of jump a little bit into diaphragms and shear transfer between diaphragms and walls in our next segment. So So just to give an update, so there are 3 big diaphragm test programs. So about 2 to 3 years ago, there was not much research in strengthening diaphragms with FRP. And a couple of years ago, Virginia Tech, a university on East Coast in US, they got a grant from ACI 440 or ACI Foundation to study the behavior of FRP reinforced concrete diaphragms. Since then, they have done about 12 specimens so far, and I'll go a little bit into that. Then Enrique and his team at University of Auckland actually got a big grant with the ministry here, specifically looking at precast diaphragms, which is very common here, but now they are kind of expanding into collectors and shear transfer and some of the other elements, and he'll go through it. And then we were working on some diaphragm strengthening as well in US. And so all of this research is now coming together to a point where we have some decent understanding of how we can strengthen diaphragms with FRP at this point. So going again back to where we are, so ACI 440.2R, which is what we currently use for design, FRP design, doesn't talk much on diaphragms. There is a task group. All of us here are part of that task group. There's a building code 440.13, so this is not a guide but a code that just got released a few weeks ago. It is only limited to gravity applications, not seismic. The next edition of this will have seismic. And again, the 369S is the seismic code, which will now talk about FRP strengthened elements as well. And the first edition of that will be 2028. So all what we are talking today is part of all these documents. So when we started doing this research, we started with a very simple test. And the question that we had was, how does multi-layer FRP ties behave on a diaphragm? We normally use 2, 3, 4, 5 layers of FRP. Most of the research that was there was done on a single layer FRP application with very thin ties. So the simple test setup that we started was, we had a block of concrete. I don't know how this works, but okay. We have a block of concrete that you see in the middle there, test specimen. There is FRP right in the middle, as you'll see the picture on the right, and you're pulling that FRP straight up. So this is a monotonic load test where the FRP goes in pure lap shear, and you're looking at the debonding mechanism of FRP, and then we did some more with anchors, and I'll go over that later. The behavior on this specimen, so again, the specimen is in the middle, there's a strip of FRP in the center. The concrete is painted white with black speckled dots. That's because of the DIC camera that's taking images, and it's tracking each of those black dots to give you a strain profile on FRP that's bonded to the concrete. So as this picks up, you pull the FRP, at some point your FRP delaminates, and once it delaminates, it continues to delaminate, and then... Can you guys hear me?
Yes.
Okay. Didn't like the video, I guess.
I think maybe you did.
I was trying to figure out if I was moving or something.
So once at a certain debonding load, the FRP delaminates, and then it just continues to delaminate. So if you think of a long FRP strip on a diaphragm, at any point where the force goes high and the FRP delaminates, you're just going to continue to delaminate your FRP right there. So why is this important? Is most of the times for seismic demands, we are almost guessing, right? We don't know what exactly our seismic demand is. If your seismic demand exceeds what you're designing for, you're just going to instantaneously lose your FRP. So this is not something that we want for seismic loads. So the next part that we thought about, and we did several hundred of these tests with multiple layers of FRP, and we found that bond is unreliable. And why do we say that? Because most of the testing that we do here is on new concrete, because all of us pour new concrete in our lab, we put FRP, we test it. But the same on when we are putting FRP on actual projects, these are 20, 30, 40, 50, at times 100-year-old concrete buildings. So there's imperfections in the concrete. So just to rely on bond may not be appropriate. The seismic demands are something that we don't know. And also on compression cycles, because FRP likes tension. Once your concrete cracks, FRP goes in tension, but in compression at that location, your FRP cannot decompress, so it just tends to buckle at that location. So if it buckles, it debonds, again, it will continue to debond. So we didn't want to rely on bond to be our sole mechanism to transfer the forces between concrete and FRP. So the next thing to do was come back and put an FRP anchor. So an FRP anchor, if you guys have not seen one before, this is what an FRP anchor looks like. The embedment depth varies depending on your concrete member. This part goes in the concrete, the dowel goes in concrete, and this FRP fan, which is what we call fan, is basically at the bottom. You'll see at the triangular port. So the load transfer mechanism goes from your fabric into your fan, into the bend, into the dowel, into the concrete. So as now with the same test, with the same FRP, at the same point it delaminates, which you see the change of color, but as soon as it hits the anchor, it just continues to pick up that force. So until a point where either your anchor ruptures or your FRP strip ruptures. So now at this point, and this is quite repeatable, you do test after test, I think we show it in the next slide, you do test after test after test, it almost delaminates at the same spot or same location, then it continues to delaminate until it hits an anchor, and then it continues to pick up.
I don't know what is happening.
Okay.
So I'm on the phone.
Let's try now. Maybe
Okay. So I'm just going to yell. I think I'm good at yelling. So when we do that, now it's kind of repeatable. We know the behavior. So at this point, it's not purely brittle response that you would expect, which if you would just rely on the bond. It's going to debond, it's going to continue debonding where you get that flat line, and at the anchor it's going to pick up that force. So this is something that we can live with, and we can kind of get those points at where it debonds and then and where the anchor or the ties rupture. The next thing that we think about, okay, now if you just put one anchor at the end, most of the time transferring all that force into one single location, you can now start breaking the concrete beam, and Enrique will kind of talk about that. Plus, if your loads are too high, you are now going to concentrate all that load in a very specific area, and you may get different failure modes at that location. So at times you would need multiple rows of anchors, especially if your forces are high. You may need multiple anchors to share the force between the two anchors. And so doing more tests, what we wanted to see is, do those anchors really work together? And if they do work together, what will be the behavior? So the one on the right, at the same location, your FRP debonds. As soon as it debonds, because now your anchor is closer to the top, it immediately picks up the force and it continues to pick up. So there is no plateau between the first anchor and the second anchor. And in a DIC video, you'll see that both the anchors work together, and it goes to a certain point, and then you either rupture the anchors or you rupture your FRP strip. So again, this is good behavior. We know that anchors help. If you put anchors together and if they're designed well, they work and they share load between the two anchors. Now we are kind of looking, okay, how far do these anchors really need to be, and how far, if you just put the anchors, at some point the behavior changes. And what you see here is at the same thing, once your FRP debonds, the first anchor kind of picks up the force, but now because the space between the two anchors is a lot, you get that flat line in between, and then your second anchor is engaged after that. So it's the two anchors are no longer working together, but it's one anchor is working first, then the force goes down, it debonds, and then your second anchor kind of picks up from that point. So you can place these anchors. They need to be close enough so that you can share the force. They shouldn't be too far enough so that you won't kind of get that load sharing between the two anchors. So here I'll hand it over to Enrique.
Thank you. So when I won the grant, I proposed the research to be divided into three big objectives. Everything that Aniket has been discussing was objective A, which is just a tie without anchors, different thicknesses. Jewelry was the first PhD student assigned to that, so we spent a couple of weeks, a few times over the last couple of years in California in the lab doing these tests. The second objective, which Mohammed is doing right now, is about the next level up. So now we don't have a tie on a piece of concrete. Now we have a precast floor sitting on a beam, and we are opening that connection. We are trying to simulate this situation where in an earthquake the column is swaying sideways, and then the beam is attached to the column, so it's going along with the ride. Depending on how far or how close we are to the column, that beam will rotate more or less. So there is a gap opening there at the interface between the precast unit and the beam that the FRP is crossing. The FRP in theory is designed as part of a 2D element, the tie, the village model that the diaphragm is, but in reality we have three-dimensional deformations in there. So the questions from the industry back when we started this project was, well, how do you know that the FRP is going to survive those deformations? Is it going to pinch the FRP in compression and buckle and break it? How are you going to detail when your beam is like 300 millimeters wide? A lot of very valid questions, but to be fair, this is overblown in terms of the scale. You can see that the column is halfway there, but in reality that angle is like 1 or 2 degrees. The deformations are minimal. But basically what we did is we copied this testing setup that maybe you have seen from previous work on just precast without FRP, where we basically have the beam clamped down to the strong floor, and then we have the precast floor with the topping on top, and we move up and down, creating a negative and positive moment at the connection. Then we have the FRP on top with different anchoring details to take that tension force. That means
6.4% strain.
That's the floor all the way down at 6.4% lateral drift.
The FRP is still holding. Anchors are holding. .4% strain and 0.7%, sorry, 6.4% drift and 0.7% strain.
So this is at the end of the test. This is tests 1, 2, and 3. And basically what this is showing is the exact same response as we saw in the ties, right? We have a very elastic, stiff initial response. Then the FRP debonds. Depending on the stiffness and whatnot, we have longer or shorter plateaus. And then at some point, the anchors are picking up that load, and it becomes a cable. It's basically an elastic spring between the anchor point on the beam and in the test case, the anchoring point at the loading end. If this was a real building, we would have one anchor there, one anchor in the next beam, and becomes a cable between the two beams. Now, I put here just to bring a little bit of context on the real design. I put here a 1%, I should say Mohammed put here, a 1% line, which is a common drift level that we have in these strengthened buildings, and 2.5. So at 2.5 lateral drift, something else has broken for sure, right? The building is not going to be usable if we reach that level. But we still have so much to go to. Even at 6.5% drift, the strain is only 0.7%, about half of the rupture strain of the FRP. This is a lot of redundancy in a system that a lot of people think, because it's brittle, has zero redundancy. And I cannot stress this enough, not because the material is brittle, the structure is brittle. Concrete is brittle, that's why we confine it, and we detail. So if we properly detail those elements, we will have a lot of deformation capacity. Now this is a little bit of detail on the first 3 tests. Basically, all of them were 200 millimeters wide, not very realistic, but we wanted to start with something easy. Anchoring, different anchoring details, different thicknesses. So this is the one layer, typical one layer product, and this is the 5 layers, quite a lot of FRP, right? and that's why the response was so steep. And then we tested different anchoring details, and we also tested the gap of the steel angle at the bottom. So whether the steel angle is right up against the floor or we have a little gap, and it doesn't make any difference at all. So we were very happy. We thought, okay, this is great, we can go home, we nailed it. Until we went to the next test number 4, where we made it wide, which is more realistic, the full width of the FRP, which is what we use in real life, no? And what happened? We broke the beam. We destroyed the beam completely. Why? Because we are introducing a shear failure plane there, and we are breaking out the beam. So we have a breakout failure. In hindsight, it's obvious, right? Hindsight is a beautiful thing. On the day, we're panicking, losing our hair, thinking what is going on here. So we thought, okay, let's extend the anchors, try to move the failure away from the plane, from the interface, back into the unit, so the FRP bonds here, as we saw in tests 1, 2, 3. That was much better, but still we broke the beam, the stirrups held it together, but we still broke the beam. I have to say, that even though we broke the beam, that happened 2% drift, I think, right? Or 3%? 3.5%. 3.5% lateral drift. So, you know, this is way beyond design criteria. Something else has collapsed for sure. Still, I don't feel comfortable designing that. So what we did next, which I don't have the details here, is we introduced a bond breaking layer there. Basically, at the interface, we installed the FRP unbonded from the concrete. That reduces the stiffness of that connection. It's basically a cable between the two bonded lines. And now the response is soft enough that we can initiate the debonding towards the middle of the span. And it worked very well. We came back to the response that we saw in 1, 2, 3. And what we are going to do next, Mohammed is going to do one more test tomorrow, but after that, we are going to include tension and rotation. Of course, this is going to make it worse. The question is how much worse. That will happen next year. And with this, I will leave it to Aniket again. Thank you.
Thank you, Enrique. So the next segment, going from these tests to now a full diaphragm test. So this is work that was done at Virginia Tech University with respect to diaphragms. And this again goes back to a little bit how we look at diaphragms in the US, of looking at it as a deep beam instead of a strut and tie model. But some of it is relevant here. We wanted to see what the debonding strains were, what is the ductility, what happens when you don't detail FRP that well, and what happens when you detail FRP well enough. So their test setup was a little bit different. They kind of put two specimens at the same time. Looking at the picture on the right here, it's about a 3 meter by 3 meter diaphragm with a shear wall on one side. There are two separate specimens, and then they have an actuator that is pushing and pulling that diaphragm specimen. Once they test one specimen, they get the actuator and test the other specimen at the other end. So the test 7, 8, 9, 10, 11, 12. So the first 6 were kind of not super relevant. There was still one layer of FRP with a lot of steel. These all concrete specimens are low strength concrete, about 20, 22 MPa concrete with FRP, with more FRP. So we have 2 layers of medium thickness FRP in one direction with anchors. And going back to my previous discussion, because the forces are so high, we just cannot put one row of anchors. You're going to just easily pull out those anchors at that location. So we have 2 rows of anchors that is sharing the force. The CD8, we put the exact same FRP as CD7, but we removed the anchors. And we just wanted to see the behavior of that specimen. And the CD9 is we took the FRP, divided it into half, put it in each direction, a little bit like how you guys do it with strut and tie here, and then just anchor all the perimeter of the diaphragm. Again, in the interest of time, I won't show all the videos, but this was the video of the specimen with no anchors. And as I play the time-lapse video, this right here is your wall. This right here is you're moving the beam back and forth. This is just the top view. This is kind of the isometric view of the specimen. And as this starts to move more and more, just maybe focus on the picture on the left-hand side. That will give you a little bit better idea. At this point, FRP bond is enough. It's kind of picking up all the force. But when it debonds, you can see how the debonding mechanism goes. So this is again FRP with no anchors. So FRP has started to debond with those chalk marks. But once it debonds, your entire FRP is just lost. In an instant, you basically lose your FRP. And then you just have sheets of FRP floating on your concrete substrate. So again, something that we don't want in our specimen. So now looking at the other ones, again, in the interest of time, I didn't have the other videos, but the CD7 was the one with anchors. You still got your shear crack. When you go underneath the specimen, you had cracks, but the failure plane was more shear friction at the end, the connection between your diaphragm to the wall. The CD8, which doesn't have anchors, you just saw that you lost your entire specimen. Once you lost your FRP, your concrete just got crushed, all the concrete just fell down. That's definitely what you don't want in your building. If your forces exceed your FRP debonds, you don't want any collapse of your building or slabs in your building, potentially injuring people. And then the other one on the right there is anchors on all sides. Again, the specimen is in much better shape, but it failed in shear friction. So at about very high loads, the connection between the concrete specimen to the wall broke, and then the specimen just started sliding. Again, something that we can control. We can reinforce that for that connection, but based on this, just the importance of detailing FRP with FRP anchors is crucial. So now that we kind of did that, now there's different ways we strengthened our diaphragm, we added all that stiffness or the FRP on our diaphragm. How do you get that force back into your lateral system? So these were tests, a series of tests done at NCSU, North Carolina State University. You have a wall there, you have a slab, and there is nothing connecting the wall to the slab. So the only thing connecting the two is this layers of bidirectional FRP with FRP anchors. And you hold the slab steady, and you can see the jack that's pushing and pulling the wall. So this is transferring your shear across the joint between your diaphragm to the wall. The same thing, this was another test we did for, we had certain projects where we had higher force requirements. Again, the same concept, you have the wall and the slab with FRP across the joint. And then this was actually a precast member with FRP, and this was just one layer of FRP connecting the precast diaphragm to a masonry or a concrete block wall at that location. And between all the tests we did, the highest connection that we had was about 290 kilonewton per meter. And these are ultimate forces. So some of the one layer connection obviously had less, but we could strengthen these up to 290 kilonewtons per meter. So you can go get pretty high forces into your joint if you again detail it correctly. So with this now, from your diaphragm, you kind of brought the loads to the joint, to the wall. You can also potentially look at strengthening concrete walls with FRP. And Garrett showed a little bit of this, so I'm just going to give a high-level picture of what we are trying to do here. So we tested 150 millimeter and 300 millimeter thick concrete walls with FRP, and this is a control wall. All these walls were shear deficient walls, so you had very less shear steel. They were designed to fail in shear, and so which is what exactly happened. So this is a control wall. This is the front side of the wall for the DIC camera. That's the back side. You got a nice shear failure in your concrete wall. And we tried different strengthening schemes. So by this time we knew that we had to anchor the wall, so we added FRP anchors. This was a 12-inch or 300 millimeter thick wall, and we just put FRP anchors with 100 millimeter embedment depth. So very less embedment depth in the wall. And what happened is, this was the control wall, you lost your concrete cover, the wall failed. The same thing happened in your FRP strengthened wall. So because the embedment depth of this anchors was only 100 millimeter in a 300 millimeter wall, the anchors just pulled off and you just lost your FRP entirely. And this didn't give you much strength increase than the control wall. So the lesson learned here was you need to go deeper and embed your anchors so that you hold the FRP, confine the concrete and hold the FRP when it gets loaded. So the next one we did was use 200 millimeter, and I'm sorry, I'm converting these units in my head, but 200 millimeter deep anchors for a 300 millimeter wall. The response was much better. We again got good capacity increase, we got good ductility as Garrett showed, and it was not a force controlled response. And this was the specimen with FRP now. So the one on the left is the front side with FRP strips on it, and this is after the test. You can see that the FRP held pretty well. It was completely delaminated between all the anchors, and this was the back side of the same specimen. So the failure mechanism was sliding shear, where you lost your concrete and the wall just started sliding. And this was because all the FRP held all the cracks pretty well, that it's confining the concrete that you lose your connection at the base. Whereas the control wall just failed in shear, which is, I think I have a picture here. This was your control wall with no FRP, failed in shear, and you changed the failure mechanism from shear failure to a sliding shear failure, which has a little bit more deformation response than a pure force control response. So again, the summary here is if you detail FRP well, it does pretty good, and you're able to get good response from FRP. So in general, going back to some of the graphs that Garrett showed, up to a certain point, your bond does pretty well. After that, you are going to lose your bond, and then your anchors take over until your failure part, which is either your FRP anchors fail, or your concrete fails, or your FRP strip fails. So just the summary of the walls is you can strengthen walls with FRP, but you have to anchor the FRP into the walls to get a response that you want. Both sides strengthening is preferred if you can put FRP on both faces, but if you cannot, you can do it on one side and detail the FRP on the walls. So the last part of my presentation talks a little bit about FRP anchors, and this is something that's very important. I think by now all of us here spoke about FRP anchors are important to get you the ductility, to get you the response that you want, to get you the strength that you want. But how do you test these FRP anchors? How do you go and get values for these FRP anchors that you can start using for design? To start with, they are different from these adhesive anchors, right? The adhesive anchors are steel rods, you're embedding it in epoxy. The response of an FRP anchor is not necessarily the response of an adhesive anchor. The big difference in a diaphragm, your FRP anchor that I showed, your force goes from your FRP strip into the anchor fan, into this bend right here, into this dowel. So there's 3 failure paths. Your bond to your FRP strip connection can fail, your joint connection can fail, and your dowel can either pull out or you can rupture. Whereas in a steel anchor, you don't have that failure mode. So this is the key difference between an FRP anchor versus a steel adhesive anchor. So for that, we need to test the FRP anchor just like how it's loaded. So this is a tie that I recently designed on a project. There's a beam on both sides. The FRP strip, the loads were not very high. This is a project in New Zealand. And the FRP strip was designed for the force. We added anchors at the ends on the strip. And how do you get the values of these anchors? So we actually did the same test where all the anchors are now embedded in concrete at that 90-degree bend. You're pulling the FRP strip, so the shaded area is an unbonded area, so you don't want any contribution from bond. You're purely looking at value of each anchor in shear. You're pulling it, and then you're failing the anchor. All the pictures on the right show a shear failure of the anchor. And you do that for anchors over anchors at different embedment depths, at different diameters, and you get the value of each anchor in shear. That now we can use that for design. Just like other anchors, there are other failure modes that you need to look at. So FRP anchor design is not simple where you just look at one failure mode. You can get a straight anchor pull out. So for that, we need to test and see what the bond stress value is for an FRP anchor in concrete, especially if the anchor is straight. And you again do that in cracked concrete as well as uncracked concrete, because somebody just before this presentation asked a question, what happens if the concrete cracks? And we do that in adhesive anchors. So something similar, we can also do it with FRP anchors. Now, in a bent anchor configuration, the same failure mode can happen where your FRP anchor can pull out, especially with shallow embedment anchors, which we have a lot in New Zealand, right? Your FRP anchor can pull off. So you need to publish those values for what your anchors are. Then the next anchor is a rupture failure. So now if your embedment depth is enough and you're not pulling off the anchor, you're going to rupture the anchor. So again, what are the rupture values for your anchors? The same thing happens in a bent anchor configuration at 90 degrees bend, where if you're pulling this anchor, your anchor can rupture right here at this joint. So what is the anchor capacity, the rupture capacity of this anchor at the bend? And then the last part is the fan, where your fan is on the FRP strip. What is the capacity of that FRP anchor fan on concrete? So you have to take all this into account when you're designing a FRP on your projects. So this was the testing data that Junri actually put together. The goal here is don't look too much into numbers, but this was for a project in New Zealand where you have 50 and 65, 75 millimeter embedment depths, very shallow toppings. So he did testing in 50 and 65, 70 millimeter embedment depth anchors at 90 degree bend as well as 135 degree bend. In H is high strength concrete and L is low strength concrete. And what he observed was at a certain point, if you are going deeper in concrete, you get an anchor rupture. AR is anchor rupture failure mode, which is more predictable. But as you go shallow embedded anchors, you now start pulling out your anchors or you get a concrete bone failure for the anchors. Again, something that we know and something that we need to incorporate in our designs. And then after you do all this correctly, right, let's say you design this perfectly, you put it on the project, so it goes for tender, and you have a contractor going and installing this on the project. How are we sure that the FRP that we have designed is now installed correctly? So this is a project in California about 3 years ago. We all thought that FRP anchors, everyone installs them correctly. And none of us checked FRP anchors on site until a school authority called DSA in California, they said that, well, you're relying on FRP anchors, they're doing so much, you need to test them on site. Proof test them on site. And well, we said that makes sense, so we tested the anchors. The first 4 anchor tests actually failed. And when I say failed, these anchors were designed for about 30 kips, and they failed in less than 10 kips when you were proof loading the anchors. Why did they fail? The specimen on the left, there's not enough epoxy in the hole, which is simple, right? You clean the hole, you put epoxy, you put the anchor. The next specimen that failed did have a puff of dust just came out from the hole. So the hole was not cleaned properly. The third test failed was the epoxy was not cured. So they had not mixed the epoxy correctly. It's 2 parts that mix into one. So again, this all seems simple enough, but this at times when contractors are trying to install more and more anchors on site quickly, you could potentially lose some quality control in that process. So once we started testing anchors on the job site, they tested about 60 to 70% of the design load. After that, about 500,000 anchors have been tested on job sites, all of them passed. But the fact that when a contractor knows that there is QC testing on site, certainly things start improving at that point. So this was an example. When you install an anchor correctly, that anchor is worth about 235 kilonewton. If you install it with some bend in the hole, it goes down to 87 kilonewton. Something else happens, if there's more bend in the hole, it goes down to 62 kilonewtons. So the same anchor in the same embedment depth, depending on the quality of installation, can give you different values. So this is something, what we recommend is to put it in your construction specifications that a contractor is supposed to proof load anchors before the project starts. And you're not really testing the anchors, you're actually testing the installation quality of the contractor at that point. And then the other 2 tests which you may already have in your construction specifications, just the bond testing of FRP on concrete and creating coupons to test the tension values of FRP on the job site. So these are some tests that have been there in ACI for a while. but anchor testing is something new that we are recommending engineers consider putting it in their specifications. This is a code report that we recently had a code report, which is an ICC International Code Council. They evaluated for the New Zealand building codes. All the tests that we showed today are part of that ICC report. So that's there now for the New Zealand building codes. And then the last thing I would end with this, we gave a lot of information in 45 minutes, 50 minutes to be exact. The intent here was not that you go tomorrow to your offices and start designing FRP on diaphragms. The intent here is you guys are going to have more questions, and we are there to support those questions. We can help with designs. We can kind of provide that assistance to your team as you look through this in your FRP projects. And the last point, if there is a project which needs some specific testing, we can test that in our lab in Stockton or in University of Auckland, and then provide that solution for that project. But that's what I had. I think we did it in 15 minutes.
Yeah, very good. Thank you. So we could be talking about this for the next 5 hours, but I was adamant that we need to cut it down, and I think it was a very good job. Thank you guys for your efforts. Do you want to be the moderator?
I want to ask a lot of questions.
Okay. Do you want to be the moderator?
Sure.
It's a bit awkward that I am the moderator and the person taking questions.
Yeah, no, that's fine.
Henry is part of ASC, so I think it would be better if you can take it.
Yeah, sure.
Thank you.
Okay, questions?
So my understanding is, so in the context of diaphragm design, horizontal plane, if you're looking at just a reinforcement, analyzing a diaphragm, so my question is about the analysis to gather your forces for your design of an FRP retrofit solution. So if you had just in situ reinforcement and it was compliant to the current code in terms of in the free NZ 311 in terms of strain limits, only seismic grade reinforcement is now allowed in terms of strain. Because it's you're looking at a horizontal plane, it's a D region, plane sections do not remain plane, stratum tie analysis is a plastic design essentially analysis. So you could, if you're looking at reinforcement that's adequately detailed, you can cap the tension limits of your ties, you can cap your compression limits of your struts. However, if you're doing an FRP retrofit, the only plastic, the common assumption is, my understanding is that now your only plastic, your plastic mechanism is the compression stress of the concrete itself. So, can you, if you do a grillage model, my understanding, to just confirm, and you're doing an FRP solution, you cannot cap any of the tension ties. And I guess it's a question, can you cap any of the compression ties?
What do you mean by capping? Sorry.
So you can actually apply a maximum compression or maximum tension to a tie in a strong tie, because it's in a grillage model, because it's an estimation of a stress.
As a limit?
It's a limit. Say you were doing it in ETABS.
It's like you are distributing a loads.
Why are you not able to do that?
My question is, are you able to with FRP? Because I guess the common assumption would be that the FRP ties are, because steel approaches yield, and then it's got then it can apply the same force of quite a substantial strain. You've got cracks opening up over your concrete.
Yeah.
You've got redistributed cracking.
Yeah.
So that's actually what you're allowed to do if you've got currently compliant steel reinforcement. But with FRP, my question, would you be able to do that?
Well, that's what I was drilling on earlier.
And you're saying that that's perfectly acceptable because actually you don't have a failure, you actually have a kind of and then even strength.
Wait, let's leave out the word perfect.
Yeah.
But yeah, I think that applies because it's the same principle, no? You design for the yield strain, 0.15, 0.25, right? And then you are assuming or you are understanding that you have a lot of deformation capacity in that steel, right? For FRP, it's not that different if it's properly detailed. It's going to debond at, let's say, 0.2% strain, but then from the point that the debonding starts, which is the same equivalent to the point where the yielding starts, you have a lot of deformation capacity. The challenge, I think, is steel is gonna, concrete is gonna crack, the steel is gonna yield, we have a strain hardening, now the crack is going to appear somewhere else. With FRP, you are going to have, once the die fully debonds, let's say 10 meters for the sake of simplicity, you have 10 meters, you have a strain of 0.2%, you have 20 millimeters. So you are going to have that strain across the whole die. Instead of reinforced concrete where you have strain in the crack, then it's not crack, you have no strain in the steel, and it's crack, you have a strain again. I don't know if I'm making my
Yeah,
point.
you get distributed cracking, and it's
So I'm going to 10 one instead of.
Yeah, so that is where the tricky part starts, and I don't think we have the answer yet, because let's say we use a high strain. Like arguably, based on these tests, you could use a 1% strain. We're still far from rupture. But at 1% strain, your beams, your anchoring points are coming apart from each other quite a bit. Is that acceptable?
Well, I think most engineers and territorial authorities would not be comfortable applying that.
You would be surprised.
Yeah, I think just to add to that, I think the goal here is what is the end goal that you want to do? It's not just a force, right? You're designing a FRP to a certain force. You're actually looking at your deformation capacity. What is an acceptable cracking that you're allowed or you're okay with, and what is the maximum crack width? Now, in some projects where we have looked at where the forces were very high, we actually added anchors in a 2 meter range, and we said, okay, let the FRP crack. At some point, your FRP will debond. Let the concrete crack there, and we have anchors on both sides to limit that cracking and to limit that crack from opening up to a certain point. So I think there's avenues to do that, but we just need to exactly know what your deformation capacities limits are and how you detail your FRP to achieve that.
So my understanding is it's open for discussion.
Yes. It's not, FRP is not like, hey, I need 400 kilonewtons in my tie, give me a design for 400 kilonewtons in my tie. I think that's the first step. The second step is deformation capacities, cracking, and all that. So
at which deformation level do you want those 400 kilometers? Are we talking about 1% lateral drift? Are we talking about the two beams coming apart from each other 100 millimeters, 50 in each side? The floor is going to collapse at that point, right? What is the acceptable deformation?
And then going back to what we looked at collectors or drags, which is a little bit different from how you do it in New Zealand. But if you have a tension element, FRP on your slab, that's continuously picking up force and putting it into a lateral system, we actually think of it, okay, we are anchoring it every so often. So as your concrete cracks, your FRP debonds, which is okay, but you have anchors on both sides. So between that anchor to anchor, your FRP will debond. But your concrete will crack somewhere else, and your FRP will debond somewhere else, and then there'll be anchors that are holding it together. Your limit state would be that you may have a completely debonded FRP strip with anchors providing that shear flow mechanism in your tie or in your drag. So I think your question is valid in the sense that we need to exactly understand what that FRP is doing, and then design that FRP to make sure that the performance is achieved.
Yep.
I look at the precast. Is there any kind of you look at the cauldron mesh in your precast units, or it was a full seismic reinforcement mesh?
You mean the actual test?
Yeah.
So we did have a cauldron mesh, but because it stops at the interface, like it does in real life, right? It's not really activated. We have starter bars, I think diameter 12 every 300,
150.
every 150.
But I mean, but I'm just saying, because the hollow core units, for example, they have a cold round mesh, and you're not relying at all on them. So your test was also like that?
Yes,
Oh, okay.
effectively it was, because even though we had cold round mesh, it was not activated.
So there was, in general, the reinforcement of the unit doesn't contribute to the,
No, the starter bars do.
oh, definitely.
Yep.
And let's say that, I mean, from before precast units, we've got a beam to beam like 7 meters, and we are putting the FRP and anchoring at 2 ends. We usually also design some kind of tandem bars from beam to beam these days for strengthening. So when the bonding happens in between the 7 meters, we literally don't have a contribution of diaphragm loads go to the FRP, and the last two only working, like at 2 ends anchor here. Is it what I'm understanding, when the bonding happened between, there's no tension transferring from the diaphragm to those between them?
I think the design strain should be equal to the debond strain. So at the design action, which we don't know if it's the real action, but that's a different conversation, the FRP is just starting to debond. So you will not have the whole floor debond. Same as for steel. We design for yield, and ignoring safety factors and all of that, at the design action, the steel is just starting to yield. So it's the same concept.
So if I can add to that, where we're moving in the U.S. is not even, we're limiting to the usable bond in terms of the designing FRP, but we're actually counting on the shear transfer from anchors along the length as well. So you wouldn't just have your endpoint anchors, but you'd actually have intermediate anchors as well.
The problem, yeah, with the hollow core, for example,
Yeah.
you've got only
That's an
50, 60 millimeter coupling, you can't really anchor.
So I'd be really interested to see if you can validate that, because where we're moving is, like you would design a steel plate with anchors between a steel plate and a concrete. That's kind of how we're looking at the FRP anchors as our shear transfer. And without having that capacity, I'd be interested to see how the bond does.
Yeah. We can anchor into the topics because we have the values.
You have the value for how much is.
The question is deeper than that, because if we have a certain die model, like if it's a grid, like the grid on the floor, each of these joints needs to be a node in a certain die model. That has a physical mechanical meaning. That means that the concrete strut that is coming from here to there needs to push against that. If we are designing a deep beam, no FRP, we have a lot of steel that is bent, and then the concrete strut is pushing against that case. And there are rules about how you design that now. Now, we are trying to replicate that with anchors that are this deep compared to a strut that is this deep. So it's not about whether the anchor can transfer the force into the concrete. It's about whether the certain die model is going to form. Yeah.
And one more point to that, and you may not always anchor, because sometimes what you'll see, your forces get too high to just anchor in the beams. So you may need to put another row of anchors before, because of the beam breakout. So that's something in a lot of projects now, we have another row of anchors in your hollow core. And if the forces are high, you may need to fill your hollow core at that location to get some deeper anchor action at those locations.
Well, for example, we've done some with high tension rod, like
McAlloy.
Yeah, McAlloy bars. It's quite common in New Zealand. And you are going to the end of the beam, you put a quite close ends clamping, so that from the beam to beam in out of plane should work, and you design the whole thing. And you're not transferring anything between the beam to beam, so in your grill edge model also, it's just full 7 meter, not connecting. So the strut doesn't transfer in the middle. So the strut is only at the corner, and you design the whole thing based on that.
I don't know if that would work, whether it's steel or FRP. Because imagine if you have, I'm going to, with the American analogy, let's say you have a beam that is 7 meters long, like you are saying, and we are deflecting it that way. And we have the cable or the McAlloy bar or the FRP from one side to the other.
What we
needs to be
do,
super stiff to prevent that from...
It's usually you put them close to column and stiffener, so load transfer with the column to column with the beam. It's not possible everywhere. So if you put it in the middle of the beam will buckle in the out of plane. So we need to be at the edge of the center.
That's not the point I'm making. The point I'm making is that cable or that McAlloy bar stiff enough to restrain the two columns from moving away?
You can put the stiffness. So you define the stiffness of the based on link elements to make that. So that is the load transfer based on the stiffness.
Yeah, a few questions. You mentioned that about the seismic and cracked concrete testing of these anchors. I'm quite curious about that. Is there anything in the works?
It's actually done. Yeah, we've started using that on projects. We actually used it recently on a project in Wellington with very short embedded anchors. But yeah, we've tested anchors in cracked concrete for both shear and tension.
So you use the same protocols of the European standards or ACI?
ACI.
So you go with the old one, so the seismic, so
yes.
the new category that it's coming up, isn't it? Categories.
Yeah, it addresses the 355.4 ACI.
Yeah, so that's the current
There's a new anchor acceptance criteria in US now for FRP anchors, 557,
yes.
AC 557, that meets the requirements of that testing.
That's
We can send that down.
that's great. Another thing, so practically the tryout doesn't happen when you have these anchors that are very shallow because they're not stiff enough. The other thing is for the rupture that you have on the between the fan and the vertical anchor.
Yeah.
Is there any requirement for the whole the top to be a certain curvature or something like that?
Yeah. Yes, we typically detail 3/4 inch radius, half an inch radius.
20-25 millimeters.
Yeah, because I remember when you do the jacketing of columns, you need to smooth the angles because otherwise they break.
Yeah, any time that you have a sudden this 90 degree, if you do this, it's going to just shear off.
Yes.
So you have this gradual radius here to prevent that.
Last things. Sorry, I said that before. I had a lot of questions. So when you have had the multi-directional anchoring, so you had like a slab that you anchored on all four edges. Yeah. So with that one, did you have a multi-directional layer? Or
yes.
Yeah.
So you had a layer in this direction, layer in that direction, and then you anchored all the layers.
That's perfect. This is the last one, I promise.
The last one before the last one?
Yeah, no. When you had the breakout at the end, because you had all these anchors too close to an out, so you had the concrete breakout because you were overlapping breakout cones. So with that one, would it work instead of having the full floor? Maybe you do strips and then you space fan out the end of the strip so that you can put more anchors that are spaced a little bit further apart. You know what I'm saying?
I do, but we're trying to make complex things simpler.
Yes,
more
that's fine. Yeah, that's fine.
I think what we try to do is make, if that is my beam, 300, we try to go either side and fill a little bit of the voids either side, so we prevent that breakout failure.
And that works really well. I think much easier to build and something that I think we understand the behavior of that concept.
And the contractors are really good at finding ways to fill those voids so you don't fill the whole thing, right? They are good at that.
Yeah. So kind of this question, you said you designed the FRPs to debond some certain strain, but with a diaphragm you usually can't predict how much strain is in a certain part of the floor. We usually use Willis model, which doesn't predict strain very well. So how would you?
Yes. So the answer is no one knows, right? But the gill-edge is elastic method, right? You are right. The ties, whether it's steel or FRP or whatever it is, are not going to be activated until the concrete starts to crack. So we design at that point, right? So we are trying to simulate that. We are trying to say, okay, now we have the yield of the FRP, and that's a physical, sorry, the yield of the steel, that's a physical phenomenon, right? It's the molecules changing, rearranging, and all of that stuff. We are trying to simulate, to replicate that with the debonding of the FRP, which is also a physical phenomenon. It's the FRP breaking little bits of concrete. So that's all we're trying to do. We're trying to equate one with the other. From that point of view, I think the similarities are quite valid. Things start to break down beyond that point because of what I said before. Steel cracks, steel yields at the cracks, and then it doesn't yield anywhere else. FRP doesn't behave like that. FRP is going to be debond here and move the debond line 1 meter, 2 meters, 10 meters, and the strain is the same between those 2 points. What I must say though is the debond strain, the method that Junri has developed to calculate the debond strain is able to predict the debond strain that Mohammed is seeing in the big unit tests. So everything is looking good. That doesn't make sense that is perfectly good because that has happened in the past. We thought we had it nailed down and then something happens. But it's looking good.
So from a design perspective, think of it like design for a debonding strain, which now ACI is going to modify that based on all this research. Design for that, but have the anchor mechanism that if your predictions are wrong and you exceed your forces and your FRP debonds, you have an alternate load transfer mechanism. So as a fallback mechanism, but you're still designing for that debonding strain, if you can.
Exactly like a steel. We design steel, but we still put hooks at the end. And we don't put hooks 90 degrees, right? We put hooks 135. And we say it's 19 times the diameter, so it's detailing, detailing, detailing. It's the detailing that gives you the right redundancy, especially in earthquake.
I guess my other question is, you said those anchors work together when you put them in series.
Mm.
So I wonder, is there like some certain force that's going to break the first anchor and then it's just going to keep breaking the next one?
Depends how close they are. Depends on the relative stiffness of the tie with respect to the anchors. If you have a very stiff anchor compared to the tie, like a very big anchor compared to the tie, it's going to attract all the load, and it's not going to let it go behind, and it's going to break the tie. If you have a very small anchor compared to the size of the tie, then it's more flexible. It's going to allow the strain to travel behind and share that strain with the rest of the anchor. But if you have 2 or 3 anchors sharing the load in, let's say, half a meter, they are all going to shear off at the same time.
So are you made to have the same amount of fibers going to the strip?
No.
No.
Few complexities there. The fibers are not necessarily the same in the fabric and in the anchor. If you go with Sika, the local Sika products, they are not the same. They are different materials. Then on top of that, you cannot equate 1-to-1 because if you have this anchor just open up like, a little bit like this, almost all of your fibers are straight. Like this is what, 10 degrees? So you are losing very little force. If you have that fiber all the way there, it's doing close to nothing. So now on top of that, we have that. If the anchor is like this, very, very sharp angle and small, so the contractor can do it very sharp like this, it's going to break easily. If it's very big, these fibers are going, I'm going to exaggerate that, but these fibers are going to be like this, with a very round angle. And then they are going to come down like that, because in here they are spread out. My point being, this is a very complex topic. ACI 440, we just passed some provisions that have certain tables, certain very prescriptive guidance on how to design anchors for U-grams. That's the first step. The next step is to get some provisions that can account for size of the anchor, an anchor that is twice the size, is not twice as strong, to account for how wide the anchors are open.
Going back to the question that you asked, when we tested 2 anchors in series, they shared the load. 3 anchors, they shared the load. The 4th anchor didn't add any capacity. So at some point, And just adding anchors doesn't mean all of them are going to share load, it's just going to shear off all those anchors at the same time. So you just need to make sure that you are using the right stiffness of the anchor to the stiffness of the tie and right number of anchors.
I spent 4 years of my life during my PhD doing FRP anchors. So if you look at my profile in Google Scholar,
But if you are designing FRP and then you come up with what force you need on the strip of FRP, how then you decide or how do you define how much anchorage you need to ensure you get that capacity?
Yeah, that's what I'm saying. I spent 4 years of my life solving that question. So at the end, the last piece of work from my PhD was a design method for FRP anchors, where you basically go to the different failure modes and calculate the capacity for each failure mode, depending on the concrete property, depending on geometry, depending on a whole bunch of things. And that has been, that it works. Anchor has tested that equation, it works. Another professor from South Carolina has said it works.
And that ACI.
Right.
No, that is public, it's a paper, it's public. Email me if you cannot find it or if you have questions. Happy to answer all the questions. That it was considered that, and the chair of ACI for 40F can help me, it was considered too complex and too problematic, contentious to include all of those equations directly into ACI 440. So the first step was to do a simplified, very prescriptive table that allows you to design anchors for one application. Now that is inside. People will start to read about it, and the next step is to do a proper, I consider a proper job, where the designer can tailor the anchorage design for its specific application.
So, but one thing going back, I think at the end, your FRP anchor has to be equal or stronger than your strip, because that's anchoring your strip. So what the equations that you're using, your FRP anchor is transferring the force from your strip into the concrete. So you need to make sure that you're at least transferring that force into your concrete. Now the next step that he's going, can you do it with one anchor? Do you need two anchors? Do you need two rows of anchors to make that transfer? That kind of goes into those equations and looking at the failure mode. But very simple concept. You have a force in the tie, your anchor has to be able to develop that force back into your beam or whatever your member that you're anchoring in, and it has to be equal or bigger than the tie itself. And then the next step becomes, how do you design that anchor to transfer that force into your concrete substrate?
You are bound to ask me Go on.
One question. I mean, the only problem that I'm seeing is when you've got the reinforcement you are anchoring, the anchors that you have, it is kind of, bound and holds things that come, and your reinforcement kind of the yield and distribute the load. But when you are anchoring the FRP, after the first part of the bond, the anchor pick up the loads and goes very high with the kind of overstrains. And then after failure, it goes to the FRP, the next part, next 1 meter. You know what I'm...
Not really, but that anchor in the middle is not developing the full capacity of the strip. So that anchor in the middle is lesser than the capacity of the strip, and it's not really transferring the full force in the strip.
So why it is going really
So the one that we showed here is that representing the anchor at the end.
Oh yeah,
and also that's a test.
Yeah.
We don't want to reach that point.
Yeah, I think if we design the two ends very stiff, but the middle ones kind of less capacity, and then it will kind of very smooth transferring.
So for example, you could design the middle anchors with an overstrength capacity of 1.1 or 1.2, the end anchors of 1.5.
Yeah, so your middle anchors are always lesser capacity than your strip, so that they can be more ductile, get that load transfer. You don't want your middle anchor to suck up that load and then fail, because that's
the test that you showed was quite scary to me.
No, so think of that's at the end. So you want to make sure that the force is all developed at the end. That's not your middle anchor. No, that's a great question. Thank you for.
If you've got a contribution all the way, and
your goal has to make sure that the entire strip is engaged, detailed, and the force transfer mechanism at your design level event is still there.
That's also what I was going to say to you. Fracture of the anchor is like 2 or 3 times the design load. Yeah, a lot of questions.
Sorry, we're trying to ask for a while.
Just ask when we are strengthening columns and walls by wrapping them with FRP, are we checking as a cracked section or uncracked section?
Is that a question for me?
Yes.
How we check it? Yeah, we're looking at a crack section in terms of stiffness, and then for strength, we're doing the typical kind of beam analogy, VC plus VS terms. And then the FRP would have another contributing factor to that. So it's crack sections and kind of beam analogy theory. What's interesting is, I'm hearing all the discussion. I think, the question about in like a diaphragm or a wall, the ability to redistribute things and count on a plastic mechanism. I think that's the same questions we're having with the strut and tie. Is it applicable? For what it's worth, on the walls, we actually use a totally different equation. There's a new equation for just unstrengthened concrete walls that we put in the AC41 last cycle. It's dependent on the shear associated with flexural yielding. So it's basically how squat is it? Excuse me, you actually get an overstrength factor relative to that typical beam analogy type equation. And that worked actually pretty well for predicting the shear strength of the FRP strengthened walls, except we had to modify one of the factors in there to get to the similar answer. But for 10 specimens or so, we were able to match that pretty well. I don't think at this point we're able to use strut and tie or these other models as effectively. The ACI 440 has a VF term that we added. That did well on some, but not well on others. So we're still assessing it out. I think that this question on shear strength and when you're counting on all these mechanisms happening together, right, it's still a little bit out there. We're trying to figure out how to treat that.
Yeah. When it's a bonds, we talked previously about you can get a deep bond length and potentially get a large crack there. So particularly if you've got like a precast unit at a beam interface, could you not get impact forces on your anchors? When you get a section debonding, then you've got movement to take up over that crack in a dynamic sense.
When you say impact forces, meaning because of the debond mechanism,
well, you've got a debonding, and then you've got a crack width that you've got to move backwards and forwards over, and you've got a certain amount of length of
It's a matter of scale.
Yes.
So if you think about the debond strain is they're relatively low. Let's say 0.3 is on the high end. Let's say it's 0.3%. We have 1 meter debonded. That's 0.3 millimeters.
Well, what if you've got a crack initiated? You can get a decent crack, say if you're near a plastic hinge with a hinge elongation, and you've got say you've got anchors 2 meters back or something. You've got a 2 meter length, and you potentially get a large movement here from the crack.
But it's about the scale. If we are using a 0.3, it's the same argument actually. If we are using a 0.3 strain, even 2 meters, the crack is going to be minimal. I think we are used to think about these problems as a reinforced concrete ductile frame perspective, where we have a plastic hinge, is hinging ductility 4, 6, 12, and the building is holding it together. With the new strengthenings, we are always going to stiffen up the building. So we are not talking about ductility 4, ductility 3. Ductility comes down to 1, 1.25. When I asked, the second question I asked after how much force we want, what displacement, what lateral drift are we talking about? And often the lateral drift at ultimate on ULS is like 1%.
So we're seeing a lot of cases where there's nothing wrong with the building, it's just the diaphragms. So you might have a ductile frame, but the diaphragm shot because they've got non-ductile mesh. And so you're literally just strengthening up the diaphragm. You can still get plastic hinges forming, and drift's not an issue, but it could still be like 2.5% or something, for instance.
I haven't seen many of those, but then it could be a problem, because not only because of what you are saying, also because the plastic hinge is making the beam grow. Yeah. So depending on the size, if you have a beam this big, and the diagram is huge, you can have a huge growth, a huge force pushing the two columns apart.
Yeah.
That's the next test that Mohammed is going to do. What happens if, on top of the deformation, we are pulling apart? Yeah, so that's the next three tests. And we only have three, so.
The impact loading would be dependent on the rate of that crack opening and closing, though, right?
Yeah.
So at least in a longer period building, you're probably your velocity of that happening is probably fairly slow. So I think that would play into what is the actual impact load. We've had that question on dampers as well come up, and it tends to not be a big impact, for pun intended, on the actual design force, because we're, the period that is oscillating over is a fairly slow period when it comes to impact loads.
I think eventually we will need to do a check table test. I don't want to do a check table test because I don't pay. But it's a lot of time. It's a lot of time for very little research output. At the end of the day, my life is measured in papers or published.
Just a quick question going to the first presenter and to the very first hysteresis curve example for the very squat shear wall, where it's the very first example, not the other walls that were falling apart. So the black line where that was like a shear control wall.
You tell me when to stop.
Just go right at the beginning.
Yeah, it was almost at the beginning. You can explain it because I remember.
For the unreinforced wall, we had a very constant shear force over a very long drift range. And then the strengthened example, you got a higher strength, but then you got a rapid degradation, and in fact you can see that the concrete must be degrading, as you say, crushing concrete. And so I guess just purely, I suppose, in this specific example, is the black unreinforced response potentially more potentially more desirable?
There's a trade-off, right? So the way we're looking at this is that we call it an emphatic ductility reduction factor would be better for the black, than the red, but you get more strength for the red. So the way we're designing is we look at an enhanced strength to that, but then we're putting ourselves in that table. There's shear stress term. We're basically saying, hey, you're in the highest shear stress term, you're probably crushing the concrete now. So depending on axial load and shear stress, you're going to get maybe a reduced end factor. So you have to see how beneficial is it to the actual design.
So you might actually, even for a particular wall, it might be better not to strengthen it at all, or do less strengthening than more.
Yeah, you may want to tune it, right? The other thing that's not captured here is there are other mechanisms that can happen in a wall, for example, sliding that take over. So I talked about it being very hard to change it to flexure control. If you can do that, that's ideal. But then if you can't change it to flexure control, which would be not only more strength, but then you get the bigger ductility. You actually do see a deformation control response when it slides. So we introduced that to the standard last cycle, depending on, again, your conditions. So there are a lot of factors at play, but to your point, it's not a sure shot like add FRP and it's all good. And that's why I think it's really key that the designer, the record, SOR, structural engineer of record, we call it in the US.
Basically
the design professional. Yeah, that has the overall project should understand this and think about that in the overall context of the design. Count on a supplier delegate design process, and not going to be thinking about all those interactions.
So there was actually another specimen that he's mentioning where you actually got a lot more ductility because it changed the failure mechanism from a shear controlled failure to a sliding shear. The pictures of the walls that I showed, and there your red or orange actually just keeps going at that point, and because you are not changing the failure mechanism.
It depends on the situation.
I should say that this is one-sided, right?
That's one-sided.
That's effectively on one side only. They are working with a challenge that these are underground walls, right?
Or even in hospitals where you don't have access on both sides or elevators.
So if you could access both sides and you could confine the boundary region well, it's a different story.
That does look a lot better. Yeah.
Now that gives you higher force and much higher ductility if you are able to put FRP on both faces. So one-sided has limitations. and we'll have to walk through those limitations. But if you have both side axles, that just improves the performance dramatically.
Because the failure here was the boundary regions basically collapsed.
This got a nodal failure.
No, this one was a nodal failure.
So it's not a
So if you
backup
cannot find the
mechanism.
boundary regions, then that is preventing the drop, and then you will continue going straight.
The existing reinforcement also contribute to this, or
Yes.
in terms of the strain, they are
Absolutely.
Yes.
they are different, but they should. How do you measure that when which one is picking up?
You talking about like what strain is in what?
Yeah.
So that was, yeah, that's not, as you were mentioning, it's a challenge to figure out what strain you use for the FRP, right? So similarly, we'd be using the debonding strain for the contribution to the FRP.
Yeah.
And then, yeah, as I mentioned, there's this equation that counts on the shear associated reflector yielding, which it's counting on your direct shear, but it's actually counting on your vertical bars and even your actual load as well in that.
If we want to cut a hole in a reinforced masonry block wall, does it work with the FRP sticking on the block wall face, or it has to be concrete surface?
No, depends on how many bars you cut and what is your loss of capacity based on the bars, but based on that you can put FRP for the lost capacity of the bars. Now, if obviously the opening is too big and you're losing a lot of capacity of the wall, the other way you can do it is how much wall is remaining. Can you reinforce that wall to pick up the loss of capacity from your opening? Maybe.
I'm not sure if he's talking about the block walls that you use here in New Zealand. They are concrete blocks, but the concrete block, the concrete of the blocks is really shitty. It's not really, 20 PA is like 10 or even less.
CMU walls.
So if you put the FRPs on these, the bond does, it peels out.
Because it's different surface.
So there is a different, so ACI 440.7, it talks about design of FRP on masonry substrate.
Yeah.
So on weaker substrate, so there are provisions, so we just use the 440.7 guide when you design FRP on weaker substrate. So there you are really going to count on your failure mechanism to be more in your substrate itself because it's a weaker substrate. So there's different design equations, much lower strains, and so you will account for that for your weaker substrate.
But from your earlier statement, you're saying that the capacity of the FRP can only be reinstated to the amount of lost steel bars that are being cut for that same opening area, and you can't go further than that.
You can go further than that.
You can, I mean, I think so. If you have a, I'm sorry for the 20 feet wall and you're cutting a 4 feet opening in that, right? You still have wall piers that are left. Can you add a drag element on top of your opening, distribute the force in your wall piers that are remaining, and can you strengthen those wall piers for the shear capacity that you have lost because of that opening? So that's one way to look at it. Now you're just making it one wall into two piers, doing like a drag strut and transferring the force into those two piers. So there's different ways you can evaluate how you would strengthen that situation.
Oh, sure, I forgot. No, sorry, I got it back. It was about the validation. So, for example, going back to the validation schemes of the ICCES or the European standards. For the validation, there are multiple tests, like 20 tests that you need to perform aside from crack or seismic, with smaller holes, bigger holes, and flooded, non-flooded.
600 tests.
Yeah, so is it something similar with these FRPs?
I'm saying 600 tests for FRP anchors. Yes. Yeah. It is. You have to do it overhead. You have to do it horizontal. You have to do it in crack concrete. You have to do it in different embedment as different diameters.
Different edge distance.
Different edge distance.
So it's a system with the
loading.
So it's a system with the epoxy and the FRP together. Yeah.
Yes. So yes, the summary here is it's not I mean, the FRP design has a lot of things that you should consider. Don't just provide a force and say, okay, I want to design my FRP for this force. There's a lot, just like steel, there are provisions for FRP and there's detailing requirements for FRP. Hopefully this was, I love the question, so hopefully this was useful.
Thanks so much.
Okay, cool.
It was one thought we had two speakers.
Yeah, sorry. We will eat it now. Yeah. Thank you. Feel free to reach out if you have more questions. Feel free to reach out if you have more questions.
Okay, yes.
Thanks so much, guys. Thank you.
Thank you.
How you all think about things and
What's going on is, to be honest, it's not new questions comes from the now we are all way that you are designing from its sequence. Yes, that's right. And I'm here with the overall project.
it's good that everybody's kind of trying to look at it from different perspectives.
Yeah, exactly. Thanks so much. Thank you. Overall, no worries. And you're the peer reviewer of your design. Yes. You're the PS1 designer, the PS2, and the overall PS2. Yes. Okay. Yes, I have another one. Okay. Cool. Thank you. Thanks so much. Really appreciate it. Thank you.
Thank you for the patience with just all my questions.
If there are no questions, there's no point.
It's trying to type. Mine is
That's my card.
Thank you. Oh, yeah. Love that. Yeah. Oops.
It's interesting to hear the questions I was talking about. You all are looking at little different problems.
Yes.
Interesting insight into about
Yeah, we had many challenges embracing the European standards. So because the New Zealand standards are all, with the ACI, it's kind of based from the ACI 28. But then from the latest revision that we had in 2017, they kind of made it mandatory to have these European testing with seismic loading for all forced installations, both mechanical and chemical. And so that was kind of a big exercise.
Yes. I think that you mentioned in terms of the testing that we are, for the all the office inside, we are still have that problem. And we are putting on a drawing and then we are going to site and usually they contacted with then you are testing.
Oh, the quality is a big problem.
So quality is huge. So
It is, and the way I tell you, the fail test that I showed was actually a contractor who's installed for 20 years. And you tell a contractor, every contractor will tell you that I've done this for my life. I know how I do it, why are you going to do it? And it's funny, the first project you test, and honestly, the DSA in California, they made us test it. And the anchors failed. And now we're like, okay, unfortunately, the first project we ever tested, I bought the anchor and now it fails. Right? So, but now we've tested it like a bunch of washpot jobs and all, and every anchor test was bad. But what happened is when contractors used to bid on a project, to be more competitive, they would put more anchors per hour, right? They would increase their production rate of installing anchors. As soon as, so in US this went to about 30 anchors per hour. Now when they put anchor testing requirements, that 30 went down to 15 because now they have to install anchors slowly. So I was just intuitively looking at it like, how come your production rate just changed because there's a quality control step along the way. So it works. I mean, the fact that somebody's seeing your work, I mean, they're all human beings.
Watchdog.
My son does that too, right? When he knows I'm watching, he tablet's done. If I turn my head, it's done.
Thanks so much, guys. Thank you.
Have a good night. Thanks so much. Thanks, everyone.
So, how do you
take the chocolate?
usually compression capacity to the diagonals and to the horizontal vertical. When I first do analysis of non-tension targets, then I look at fields on where you see where I've got generally very similar tension targets.
Yes.
Or there is an already mesh, and then I would limit those to that limit. Then I leave the tension ties to something I'm designing, and usually say you'll call monitoring building, they're going to get very high levels, which are and then I just do the drag bar type and drag bar those particular regions.
Yeah.
I leave those unlimited and say, as a community, I just need to know how many bars I need and
I don't remember
the question is with the steel elements,
sure.
Current strength ability? Well, yeah, because it's an old steel, it doesn't have current strain capacity of seismic things. Yes, but so I mean, first pass is just assessing the existing diagram. See if you ever use. That's good. What I am. Yes. So then you would, if it's just cold draw mesh, now you can't the assessment guidelines. You're not using it at all.
Yeah.
So.
Is that true also?
Yeah. So what I mean is, as soon as
Does that mean?
I don't know what to do with the old.
I don't have a paint.
Steel.
Don't you need, oh no, you finish with two.
Oh,
no testing.
Yeah,
no more testing anymore.
Yeah, but I think finish testing is I think it's
Every precast topping So the question is, if you've got a regular building,
I think it's not most
have
of
you got
I think
enough,
all of it
can you use the existing that you have in the steel
Yes,
beams,
yes.
so just use
We test
the
it all.
topping as and between as a vibration
Yeah.
If the existing steel is not,
and
it's a type that is low strain,
So how long will you,
then if going back to
we
the
use a
solution might be
so we
steel
found
plates.
four
And
times.
then the question of that is, can you, which is what I was thinking, can you now still limit potentially?
Yes, right, actually, it's,
because without that
Well,
data,
if you're doing an
the rest of
FRP
it
that's
wouldn't have.
very well detailed,
yeah, for the first
underlying
part,
FRP
for the
is
wrong
different.
one,
Presumably,
base one, we proposed it on now already.
a lot of the,
So that's it's
building plan, we had
that company.
Yeah.
That's
So if you end up
Yes, in
situation
terms
where
of
you don't have any, and then the FRP.
Before that,
is
everybody
leading to
uses
situations
guessing.
where
Yeah,
it's
yeah.
cheaper.
Guessing, you want to do it, how we're doing the.
Five years back.
So only 3 years back.
Yeah, depends on the loads.
Depends on the
If you stick to advanced training,
Area 5 then coming to fast. That's all it was.
I remember.
Yeah, they proposed it on one down the bridge,
Now, if they did it, now it was always area of average cross-section area and that angle of effect. Angle and that was even the depth of effect was also the angle and the area.
Yeah, there was, I mean,
that's what it
basically there was
But then it's nothing else.
Yeah.
Even for sharing the load, you have like ACIs blocking out. And
we have a lot of them, let's say, because the FRP, let's say, are 20% higher. FRP, so now it's, for example, I'm making up one. So you have a lot of them.
And also, people.
Now, what happens after that?
Yeah, we have to do, it's just life safety, because everything else is
very
so damaged.
I think the bigger question.
No, just to go back. The only
I think the only, yeah, I think
is the FRP is fully recorded. And then English sound goes on straight. Because why does it want this? We have no reform. As we said, it's an open.
I'll pull it out for you.
So what happens?
There's only one that
It
has
knows at some
some
point, we don't care what it is, because we think it's got this.
language.
With FRP, we don't know where it's going to be.
Well, I mean, we just, the presentation was pointing out that it's actually, the hangers appears to be.
But we don't know that.
There was nothing
Oh,
else.
it's temporary.
You wanted something that
Then what is I spend the
No,
last year?
no, because one of the reasons.
and I know that
shear
I do have a
cracks,
design
when you do
that
one
is very,
crack,
very basic.
one defined
Very,
crack,
very
if that crack was in place,
fat angle.
over a diaphragm, we have no idea how
And remember those days.
are they all uniform cracks, are they inclined, are they different? That's why the difference is in the shear cracks. We assume sound united straight over four height. If the cracks are in the exactly perfect unit.
Yeah, but the thing is that external side is a long boundary. So if it works, it just proves at the worst case, it's the minimum.
That's what I'm saying, you have to
It's the
do
minimum.
only the ultimate.
Yeah, it's the minimum of infinite other solutions. It's the worst case that is stable. So with straight tie, you can have nominate different mechanisms. Some are more efficient,
The lot of
they will lead to tighter cracks and more distributed smaller cracks. And some are less efficient, that lead to smaller larger
Yeah,
cracks.
you can't.
You can look at
In
different mechanisms.
shallow
So if you have FRP solution that you got this sort of thing, you can now apply compression to your compression stuff as well.
So once you design the FRP, in my opinion, the point is to get to know if all of it's
No, you would do your design and then try and design the FRP based on your assumed mechanism.
And then it's just depending on what strain you're using.
Well,
That's what I'm trying to get at.
FRP.
But that's what I'm trying to do, is trying to say. We are trying to equate the elastic point still is yielding, we're going to yield there. The elastic point in FRP is the only one is going to be wrong. We're trying to equate the two as much as possible. What happens after is
Anything
after the design. But the same happens with steel. Like if we use maybe this one is not just steel, it's the same. What happens after the yield, right?
It's just getting it past the peer review.
Oh, did you? I think I've seen you in this. Yeah, no. And what about
So that's what I said. When you did the papers, so who did the analysis for G?
I would like to bring it.
You wouldn't need to.
You don't expect me to.
If you're not doing it now, it's the design yourself.
There's a whole bunch of
You
people that
just need to go to the slide.
What can we do to have the full right, because right now they're so.
We are going to give you that.
When you get there,
And then I'm going to go back to you and tell you.
Then if they really are teaching them well,
Even before
they
the
What's funny, outside of steel frames, outside of steel frames, things are dated. They do really good expectations, but now we are not going to hold out. You mean functions, that's why until you get to like fiber up.
So what I want to do is add I discussed it with both a roadmap of conference. So
most organics are
that was one of as it opens, it's a very specific area. Round enough to even if it cracks, it will still crack so much, which is acceptable to the
We have to
yeah, you know what's happening? Who say, hey, we use CVG, how do you use that? They use their local standards, come up with a force, then find a capacity. And I want that. I love the omega, scale it up. But if you don't enough,
But if it's manageable, then how do you provide that solution?
Is that something if I did the roadmap, if you use this in you want to educate people, don't stop them from doing it, but we're like too low.
We are actually testing next year. Basically, we have a 6 meter they have to limit the stick.
So what we take is especially coming from
So where do you think this is falls the other side?
So there's a California, there's an international agency, but also in the
We've got all of this, yes. And that's the chance. Although we do it, we still have the stepping stone by size one, based on all of this.
So basically, like, it's a power table definition, it's not 75%, it's
on the basis of
1 or 2 year more likely.
yeah, exactly.
That's the whole.
So it's instead of like your design level, then
think about the year. If you want to scale,
It's actually says
that what's being done is in there.
So literally what is it?
You can do that.
I think we put your point to the 40 side. Now it's the same, your house is in terms of your results, how you design that has okay, this is a perfect design.
Because if we go now,
Omega here, I can imagine.
Something. But would you mind when you get otherwise, you send me that page?
Yeah.
And so I can prove that.
Yes, I think we put good,
I feel like there's a good but that's only like the thing is my solution the whole thing has to move, the diaphragm has to move. So there are a whole bunch of ifs, but you can use my position one of the hours. So that's with the nature and the presentation, 75%. What we like analysis. Yeah, what we're doing now is so I was doing some yes. So I put it out there, and you might want to look at it. Know that technically something else now. There's no and our first step is when we So, alright, yeah, so we'll see what tomorrow. The reason we do one is more because it's not. Alright, we'll see what tomorrow is.
Awesome. That's
very good. Alright, take care.
So have a good evening, yeah?
Yeah, you too.
So yeah, it's very complex.
Once they do the design, you can't make that assumption. You have to do the, you have to do the you can't then, once they give you a detail design, you can't just go, oh,
work in the same office?
No.
Yeah, and it's a very much, depending on the project, it's very much an interactive process. Like this project that I was mentioning before, it's Palmerston, and they gave me like 2,500 kilonewtons. It's not going to solve. We have to go through that 2 or 3 times.
Yeah,
and maybe we cannot make it.
What is the project?
They had, well,
and try to concentrate forces in a very small area.
Yeah, they had this building, so it's quite good. There is walls there, because of each corner, and then they have cores there and so what they did, right there, outside, and try to put one more tie there in the middle. Just came down or something. So it's much better. It's still not water. Try to do 2 times. And now it's working. So now we can move to the detailed design because now we can very quickly do a preliminary design. And for one thing, can price it. And then the owner, the police in this case, can say, okay, this is acceptable or not. We'll be waiting for the next opener.
So I guess the moral is just straight away assuming a 2 meter or 1 meter
assume 5%. That's a better way of so I think
desirable.
This is the area where carbon swap is basically production.
Yeah, that's why we did only 30 degrees, 75 or something.
Yeah, 50 years embedment.
It depends. Like if we have, this is my bin, we have hollow core there, and then we go in there. We might be able to call the chain. We might be able to fill that and put anchor there, and those might be shown. If it's in the other direction, when the bin there, we feel the whole thing.
The problem with filling holes causes other issues now for holes.
Yes. Yeah. So I come back to the lateral drift. So at 0.5%, we start seeing cracking of the walls. Right? 1.5, those cracks are wide enough that you cannot rely on the shear strength, shear capacity of the are you not
Well, I think for a lot of old buildings, they seem to have like it depends on the
So you want to use this with that.
all the buildings I also like these all of them, you don't have something to strain them. Every time I ask, they never told me that. I'm thinking, do I need to create some
you could also, but there is nothing. I don't want to.